Hello and welcome to our new session in our deep learning course. Basically, today we are going to focus on the modeling part as we are going to do the sentiment analysis project, which will need a recurrent neural network as its building block in its module. So basically, we are going to understand some of the recurrent neural network derivatives like the GRU neural network. So basically the GRU is, as we have discussed earlier in our first lecture in the theory part, that it behaves in a very faster way than the LSTM and more efficient than the RNN. So basically we're going to use this as our building block of our recurrent neural network. But first, to understand, we need to make it a using of the GRU not just as a black box, but also to understand its nitty-gritty parts behind the scene. So basically, this part's objective will be to build a simple recurrent neural network for the sentiment analysis project, which will be 3 layers most of the time, because we need this GRU and this embedding layer and the linear layer. So let's get started and understand what these 3 layers mean. By the end of this lecture, you should be understanding how to build a recurrent neural network as you wish. Okay, so let's start. Basically, the first layer is the embedding layer. So embedding layer is nothing but giving each token a vector. So as you can see here, we have a matrix where this matrix have 2 dimensions. The first dimension is the number of tokens. The second dimension is what is the length of the vector for each token. So for example, here I have a token with a numerical ID of 12, and this token had a vector of 300. So each token here has an independent vector with 300. Okay, why we are going to embed these tokens? Because basically we would like to have some similarity in these tokens. So the embedding matrix or the embedding layer will be learnable parameters. Like this embedding will be enhancing as much as we are going to train our model, because it will give some you can say clustering or similarity with these tokens. So tokens with similar meanings will have similar numbers or similar vectors for now, because we have here give random numbers as the token ID. So the embedding matrix will give this flexibility to add a similarity dimensioning or a whole vector, which this vector should be similar to other vectors which got the same meaning. Okay, so tokens here are being flattened on this dimension, and the vector for each token is the second dimension. So for example, if I have a review which is good quality dog food, this review is a positive review for dog food, and I will be removing each word into its number, and this number will be this token numerical ID. So 45 for good, 12 for quality, 77 for dog, and food for 99,000. So this vector is 1 by 4. Okay, I will be going to give each vector a whole, give each token a whole vector, as you can see here. So 45 token will have this vector, which is the vector of 45 in the embedding matrix, and the same for 12 and 77 and 9k. Okay, so I'm here adding a new dimension. As you can see there, now it was a single vector, now it's a matrix. And in the next part, we will be adding not a single review, but a batch of reviews. So this batch of reviews will be the same way. We will give each token within this batch a vector. So instead of just 1 by 4, it can be 10 by 4. So I have 10 reviews, and these reviews have they might be different lengths, as you might say. We have truncated the length of the tokens, so the reviews might be variable lengths. So let's say we have adding the sequence length of 40. So each review will be 40 token, and then after we apply the embedding layer, so it will be 10 by 40 by the embedding, which is 300 dimension. Okay, so for example here we have this two-dimensional matrix batch size by the sequence length, which will be adding to paddings, as you can see here, and this length of the sequence will be 40, and the patch is 32. So basically we have 32 review, each of which have 40 token. Okay, including the padding, of course. And after we apply the embedding, so this output will be 32 by 40 by 300. So it was basically batch size by sequence 32 by 40. It will be 32 by 40 by 300, which is the embedding dimension. So that's important part to understand the dimensionality of each input and output, because basically the recurrent neural network, or the GRU, takes a three-dimension matrix. Okay, so if you want to, for example, apply a GRU for time series analysis, so you need to make the time series into 3 dimension. Okay, it should have an embedding layer also, because this review will have a single dimension like the sequence length. So now we are adding this embedding layer to add a 3 dimension. So because the GRU will have this 3 dimensionality. So before going to the code, I will show you the GRU layer. As you remember from the previous lecture, this GRU cell, it was basically running through these two inputs, that it takes a hidden vector, and the current input, which is basically the embedding of the review, like the X embedding, which is this vector. Okay, so it takes this matrix as its input. Okay, let's okay, so basically it takes embedding of the token, of the embedding of the review, and the previous hidden layer. Okay, and also, as you can see, it will not be the whole embedding vector. It will be each token will have its GRU, because as we have discussed, the GRU is not parallelized, so we cannot insert all the review at a single instance, because the review consists of multiple tokens. So each token should be inserted into as an independent GRU, as we are going to see in the next visualization. And after this, the output of this token's GRU will be inserted into the next token's GRU. Okay, so basically this is the overview of the GRU itself, but let's see how in detail this works under each embedding, after each review. So let's also collapse the code part for now and understand the theory first. So in order to understand the single layer details, so this is basically what it's in this GRU, a huge GRU box. So basically it's a sequence of GRUs. Okay, and each GRU will take a single token, but for the whole batch. So for example, if I have a batch size of 32, so I'm giving this first GRU the first token of these 32 reviews. Okay, the embedding of them, the embedding of the 32 token of the 32 tokens. Okay, of the first token of 32 reviews, and giving the output. As you can see here, it has 2 outputs and 2 inputs. the output will be the same vector, an output vector here, and the second output will be this hidden vector, and it will be passed through the next tokens GRU. Okay, so for example here, if I have a 40 sequence length will be 40, like I'm having 40 token in each review, so I should have 40 GRUs inside, and this 40 GRU will be, its output will be the final output that I will be inserting it into the linear layer. Okay, and I'll be having also a concatenated output for the whole hidden layers before. So the GRU will be combining all these outputs in this matrix, which will be called the output matrix, and also giving me another hidden layer, which will be a batch size by the hidden dimensionality, which is 128 that I define from my side, this 128 dimensionality. And this vector will be, the vector should be added to the linear layer. As you can see here, I'm taking this vector, or I'm taking the last output vector, like I will be taking this last vector because they are actually the same, and then passing them to the linear layer. So the linear layer is also can be treated as an embedding layer because it's nothing but a matrix. Okay, and this matrix takes a two-dimensionality, producing two dimension. Basically it will be having the linear layer will be transforming this GRU hidden layer, hidden vector or matrix, because we have a batch of hidden layer, and then transforming it into the output dimensionality, because for example I have here the dimensionality is 128, so I need to transform this matrix into how many classes do I have in my project. So the food review is having a positive or negative. Okay, so the linear layer will transform this 128 dimensional matrix into two dimensional matrix, which will be giving each of the reviews in this side, this patch, whether it is a positive or negative. Okay, so as you can see here, it is taking this hidden size as its input, and the output of it will be the number of classes that we have. Okay, but let's get deeper into the GRU again, because GRU have many parameters that we didn't discuss. Like for example, we will have this batch, we will have this number of layers in the GRU, and also the bidirectionality. We can have bidirectional, as you have understood it from the theoretical part. We can have two directionals, not only a single direction. Like the last GRU can be its output can be the previous tokens, not only the previous tokens, but also this second GRU can take the input from its forward layer, but this will be need to be a two layers, as we will be seeing in the next slide. But now let's go to the coding part, and then we need to go to the more details of the GRU. Okay, so basically in order to build this embedding layer, let's also collapse this. Let's start here and collapse this part and start from scratch here. So basically I'm defining some constants inside this cell, and I'll be using them instead of writing them again. Okay, like these are the constants that I will be using. Okay, and let's now build the embedding layer. So the embedding will be taking an input of the vocab size, how many tokens I have in order to build its first dimensional, as we have discussed here. It needs two inputs. How many tokens I should be increasing my matrix, and what is the dimensionality do you need for each token? Okay, so I need to give it these two inputs: the vocab size, how many token, and the dimensionality of each token. Okay, so basically I need to give it this v, which I here defining the vocab size as 500, just a toy number, and then we are giving it the e. What is the e here? Is the embedding dimension. Okay, so this will be the embedding layer. After this, it should take an input like this input will be an input x. This x should be two-dimensional, the batch size by the sequence size. So I need to create a random input, for example, torch.rand, but it's not any random number, because this random vector, random matrix, I'm trying to define now this matrix here. This matrix. This is the x batch size by the number of tokens. So this matrix is not any random number. Its numbers are between 0 and the vocab length. So I cannot be increasing or generating any random number beyond this vocab length, because it will be searching for this token inside this embedding matrix. And if it didn't find that number, because it's basically random now, and it didn't find this number in this embedding matrix, it will generate an error like this number doesn't exist. Okay, so basically I'm here defining a vocab of uh, of 500, as you can see. Let's start it. Yeah, of 500, as you can see here. And this random dot rand int, because I need to define it as rand int, because I need to have a low value of, for example, 1, and a max value of the vocab size, and its size will be the batch size multiplied by the sequence length. Let's see. Okay, rand int. Okay, so it have a direct example. So basically it have this, it will be generating this matrix, and I will be giving this matrix to this embedding layer, and here I will take this output and check its shape. So basically the shape will be nothing but increasing the dimensionality of this by the embedding dimensional, which will be 300. So it will be 32 by 40 by 300. So if you increase this number of vocab, like for example, I have applied here by 5, so it will be higher than the vocab. If any number generated inside, okay, so I can see here index out of range. So it didn't find this number or which you generated inside this input, because it's beyond the vocab size, okay, as we have discussed. So it will be searching inside this embedding matrix for these tokens, and these tokens should be within this range of the vocab length. So now we have this three-dimensional matrix. We can really have a green light to the GRU, or recurrent neural network. So we are going to build this GRU layer with the simple inputs. As you have seen, it takes the embedding as its input, and the output of it will be the hidden size. Okay, so this we call it the GRU, and this GRU will take this X embedding. But an important part here in the GRU we need to define is basically we need to tell it that we are having the batch size as our first parameter. Okay, because it expects it as a second parameter. It takes this 40 as the batch size, but basically we have 32 review, not 40 review. We have 32 review. Each review will have 40 tokens. Okay, so we need to define, we need to tell this GRU that we have a batch first flag set to true. Okay, so now we will be having this GRU output. As you have noticed here, we have two outputs, not a single one. Basically, the output of it will be a matrix and a vector. So as you can see, it takes an input, this embedding matrix. It takes this embedding size of this matrix. It takes just only the 300, and takes also the hidden dimension, which will be the h, as we're going to find here as 128. Okay, so basically let's collapse now the details, and let's save the output of this GRU inside two variables. Let's call it output. Basically, sometimes we don't need to use this output. We use only the hidden vector. But just for curiosity, we need to see their shapes. As you can see here, it takes 32 by 40 by 128. So it takes all the 40 vectors and collapses them, combines them in a single matrix, and then it produces the last output hidden layer into a hidden dimensional vector, into this vector h. Okay, so this will be basically our input to this linear layer. Okay, so the linear layer we are going to build here, as you can see, it takes an input which will be the how many, as you can see from this graph, how many dimension in the hidden layer and how many classes do we have. So these are the two inputs for this layer. It's just like the embedding layer itself. Okay, so it takes the last dimension in this vector, because we are going to insert this vector, and also we can slice. I can also take this last vector. As you can see here, I take the last hidden layer in the output matrix, so it is the same as taking this h vector. Okay, so the linear layer will take this h, and the output will be the number of classes, which I'm saving here as O, or it is C. The number of classes I have in the project, it should be 2. And then let's call it FC, fully connected layer, and the input of this FC will be H. And let's see the predictions. Let's call the prediction of this the shape of the prediction. It is 1 by 32 by 2. So basically, sometimes we don't need this 1, because we know that we only care about 32 by 2. Like, we need only this matrix. We don't need this extra dimensionality. So we use something called the squeeze. So squeeze, like, for example, this is the shape of the edge. If I do squeezing to this dimensionality with the first dimension, so I'm squeezing the first dimension, so let's see its shape. It will be 32 by 128. Okay, because I'm squeezing it to be inside this two-dimensional matrix. Okay. So the squeeze will be reducing the dimensionality, as you can see. So now let's go back to building our objective. As you can see here, we have these three layers. Each layer will be inserted into this forward. The main part that we cannot do here is a sequential approach of writing this number of layers, because we need to neglect this output and only use this output. So it is not the input of this layer will be the output of the previous layer. It is not that simple as we have in the iris classification project that we have discussed earlier, because each layer will be sending its output to the next layer and the full dimension, the full output will be inserted. But here we only need to choose this hidden layer, or maybe also you can do like you can have flexibility not only to be uh, using the last layer, because you can also use for example the last two layers. Okay, and if you apply like for example if you apply here if you can call it this O, okay, or H2, for example H2. So the shape of this H2 will be this 32 by 2 by 128, and I'll be inserting this inside the number of inside this linear layer. But here you need to understand that you are taking two hidden layers. Okay, so if you need to insert them into the linear layer, you need to make it in a two-dimensional way. Okay, so basically we need to I'm showing you the neural network will be very flexible to insert any dimensional any input to the linear layer. You are not just taking this last hidden layer or anything. You can take anything actually. Like you are not you don't need to take only the last output. You can take also the last two outputs, the last three outputs, the full output matrix, and push it to the linear layer. Of course, you need to flatten it in some way. So it's an open area. You can do anything. Okay, you can take any output from this matrix and use it as the input for your linear layer. Okay, so for example here, let's collapse this for now. For example here, I'm not taking only the last layer, but I'm taking two hidden layers, like from the output matrix. And then I call it H2, and I need to insert them to the linear layer. For example, if I inserted them here, okay, so it have these multiple layers, 32 by 2 by 2, but it should be like I need to collapse these two hidden layers inside each other. So basically we need we need to just reshape this hidden layer, hidden H2 matrix in some way, like for example I need to take only the first output and multiply the two outputs. Okay, I remember it's called transpose maybe. Okay, like it is like view or something. Okay, or maybe I can do a squeezing of it. Okay, anyway, like we try to for example collapse the two dimension of this three-dimensional matrix and push it to the linear layer. So I think it can be called the reshape. Okay, and this value of the reshape should be reshaping this dimensional into for example 32 by -1. Okay, okay, so it takes an input. It's not the index of the vector, but it takes the dimensional of this matrix. So basically what I have done here is to use this 32, and this two-dimensional will be collapsed or flattened within each other. Okay, so this will be the input of your linear layer. But for example, now you don't have the h as your input, but you have h by 2. So basically you need to multiply this by 2, and then you give this the h2 here, and then okay, let's check this. Okay, also there is 32. Sorry, I didn't reshape it correctly. Let's call it h2 here. I did, because the reshape is not implicitly changing the dimensionality. Okay, so now I have the same output 32 by 2. So I'm showing you how you have the flexibility to use any number of input, any number, choose any hidden layer. You can choose like I need the first, the second, and the fourth hidden layer from this GRU, and then inserting it like I need only this and this, the second and the last. So you can use any type from your if you need to do any research in that. Okay, so the PyTorch framework give you this flexibility pretty well. So it's basically focused on the researching part. So it gives you can actually change anything. Okay, so you are not in a train way. You can move in any directions. Okay, so let's get to another part of this GRU, which is if we can add two layers. How can we add these two layers? So we just insert into the GRU definition num layers equal to 2, and set the num layers to 2, and the number of layers will be generating the same two outputs, but the hidden size will be 2 vectors, because each layer is generating its independent hidden dimension, each dimension. Okay, so I have elaborated it in this diagram. So basically we have this GRU, this is the first layer, and its output will be generated to be inserted into the next layer. Okay, so the next GRU will take the output of this previous layer, and now it will be generating this output. So this output basically will not be the same as this first hidden, but it will be the output of the second hidden layer, the second GRU hidden layer. Okay, and the concatenation of this is actually the concatenation of the second layer's output, or the second layer hidden vectors, all the hidden vectors of second layer. Okay, and this will be the last two layers here will be added to the GRU as the hidden layers of output. So it takes hidden layer here and hidden layer here, and this will be the output. So dimensionality will be 2 by batch size by hidden size. Previously it was just 1 by batch size by hidden size. Okay, so now if we need to have a bidirectional way, so the bidirectional is to have a forward and backward directions in the same GRU cell. So basically we are going to have two layers as well, each of which will be having a separate direction. So the first layer GRU will have a forward direction, and the second layer will be propagating this X embedding matrix in the opposite direction. So instead of taking the first token, it will take the last token at its first input. So for example, this GRU will be taking the last token as its input and propagating it in the opposite direction. Okay, so these inputs will be inserted for the first layer of the GRU and be passed in this way, and the output of the opposite direction will be also concatenated to the forward direction layer, okay, as you can see in this diagram. And also each output will be exported into a separate matrix. So the matrix will be like the two matrices here will be combined together. So instead of just having batch size by sequence size by hidden, it will be batch size by sequence size by the hidden by 2, because D is directionality, and actually it is a flag in the GRU. It will be true or false, so we can set it to true. If it is, so we are increasing the hidden by 2, multiplying the hidden size by 2. Okay. So that's, for example, this bidirectionality. And if we have two layers and bidirectionality, we will be having increasing the size of the output matrix and also increasing the number of layers of the hidden size. Also, this dimensionality will be added to the number of layers in the hidden size. Okay. And all these variations of bidirectionality number of layers, these two variables, they can be played together, and you can, as correspondingly or accordingly, you need to adjust the input size of this linear layer. Because for example, if you have added two layers in the GRU, so you need to define this h by 2. If you added 3 hidden layers in the GRU, so need h by 3. Okay, if you applied 3 layers, if you applied two layers and the bidirectionality, you need to have 4h, because you have, as you can see here, so we have 4 hidden vectors. Okay, so as which as you can modify the GRU, you can as well modify this linear layer. Okay, so for example, let's start by defining this GRU with different sizes. For example, here I have this number of layers. I can set it to 3, for example, and let's see the output shape. As you can see here, now it is 3 hidden layers, but the output dimension as the output matrix is the same. Okay, and I can also modify this output to be as well. Let's take this away and reshape this hidden. Okay, it's not h1, it's h only, and reshape it as well as the same way. So it will be basically taking this. Okay, we need first to transpose this. So as you can see here, we cannot apply the sequential anyway, because we need to first transpose this. Okay, I think this will be 3 by 28. Okay, so it's right. We don't need to transpose anything. We just take this 32, or because already we know this patch size, right? So we need to just take this P. It will be also as input to our model. So you need to take it as input, because we are going to use it in this hidden reshaping if we need to reshape this, if we need to add any other parameters in this. Also, if it is bidirectional. Okay, before we going on, we need to apply this change as well here. This will be the number of layers. So number of layers is 3. So I need to define this as L to be 3 to make it general. And here is the output, and here is the batch size, and I need to multiply this by L. Sorry, I need to multiply this by L and give this as output. As you can see, the output here is batch size by 2, very normal. Also, if I have this bidirectionality set to true, I remember it is bidirectional true. Okay, okay, it is right. As you can see here, it is 6 because I am multiplying this L by 2. So I call it, for example, D, and let's call it true. So here now I need to multiply this by number of layers by 2. And also the same way will be here applied because the D is true. Okay, so as you can see, these two variables will be changing as well this hidden output. So you need to take care of this as we are going. As you can see, also bidirectional will be changing the dimensionality of the output matrix because it will be multiplied by 2 because there will be concatenation of two directional vectors. Okay, and combined together. Okay, so now you have understood the main concept of this GRU. So in the next lecture, basically we will be building the model as well besides the dataset and the food review, and also might be having a separate lecture for the tokenizer because we need to use a paired tokenizer instead of using this from scratch. We have built tokenizer because paired will be much efficient and more fast. But I wanted to do this encoder lectures in order to give you overview how this being built behind the scene. Okay, I hope you understand this lecture pretty well. Hope you also try to use maybe the LSTM, as you can see, or even the RNNs, and all these are recurrent neural network. So you can also choose, try to play with them and try to hack on part of this coding it on your side. Okay, see you next lecture and goodbye. Thank you.